everybody, and welcome to our first Brown Bag webinar of 2026. My name is Tess Konovich, and I'm the Scientific Marketing Manager here at Earthshift Global, and I want to thank you all for joining us today. We're excited to host today's webinar, The Footprint of Semiconductor Chip Manufacturing. Our speaker today is Cédric Rolin, Manager for imec's Sustainable Semiconductor Technologies and Systems Program. He holds both a master's and a Ph.D. in material science from Université Catholique de Louvain and spent 15 years advancing research in flexible electronics and nanoimprint lithography at imec and the University of Michigan. Over the past 4 years, Cédric has focused on driving sustainability in the semiconductor industry with a particular emphasis on assessing and reducing the environmental footprint of manufacturing processes. We're so excited for your talk, and we'll be hosting a Q&A session at the end of this talk. So our audience, if you can put all of your questions during the session in that Q&A feature, I will be reading them aloud at the end of this session. So without further ado, I'm going to hand it off to Cédric. Thank you for being here, and I'm excited to learn from you.
All right, thanks a lot, Tess. And let me get started. This is actually the outline of the talk, and those are the topics I will discuss today. First, I will address what are the areas of concern from the semiconductor industry, and then I will take a dive into the imec.net zero model for integrated circuit chip manufacturing. And I will also discuss then a topic of environmental scoring that is a spec to guide innovation, and then I will conclude. But before starting with the first topic on the menu, I just wanted to give a very quick introduction of what imec is. So imec is actually a research center that is specialized in semiconductor technologies, and it has actually existed for 40 years now, and has been actually playing a very pioneering role in the development of semiconductor technologies. And so today in 2025, imec has more than 6,000 employees of more than 100 nationalities. The facility is actually, or let's say the headquarters of imec is based in Leuven, that is close to Brussels in Belgium. And you can see here an aerial picture of the campus where we are working on. That actually contains multiple fabs with a total of 12,000 square meters of R&D infrastructure. So R&D clean room with more than 250 tools, and that would include 200, but especially 300 millimeter tools operating around the clock. And we are essentially the biggest semiconductor R&D lab out there. And we are working with pretty much all the companies that are across the semiconductor supply chain. And so within imec, we have multiple programs developing multiple type of technologies, including the let's say future technologies that will come on the market in 10 to 15 years. But I am actually the program manager for the SSTS program, that stands for Sustainable Semiconductor Technologies and Systems. And that program really has a focus on sustainability, where the core mission is to help the semiconductor or the IC manufacturing value chain, so integrated circuit manufacturing value chain, to reach its environmental sustainability target. And so in the program, we have 28 company partners, including big system companies, so big fabless companies. We have a fab and foundries, so the makers of the chips. We have the material suppliers and the equipment manufacturers who are supplying actually to the foundries. And then we also have interactions with government for public funding, with industry associations, and also with academia and other research and technology organizations with whom we collaborate in order to push sustainability in our industry. And so now moving to the first item of the menu for today, that is to state what are the areas of concerns for the semiconductor industry. The first thing I wanted to flag is that our industry is really complex, and we are actually producing some of the most complex complex mass-produced objects. And maybe just to take a quick look at the life cycle of making a chip. Essentially, maybe the best point to start here are the people who are putting electronics products and goods on the market. They are the ones who are going to specify, what are the customer specification, what the chip should be doing, and then it will move to design, where engineers are going to specify in order to meet those customer specification what type of chip would be needed. The design is then pushed into a semiconductor foundry to fabricate the chip. The chip will then be, or the wafer after testing, will be cut into a number of dies, and the chips will be picked out and assembled into a packaging. And then the packaged chip will move into the maker of the final product, and it will be assembled into a product to come into the market. And if we are zooming into the semiconductor foundry, essentially semiconductor foundries, and here this is a sky picture from a TSMC Fab 12 located in Taiwan. It's actually a very large fab that's producing multiple logic technology nodes. And it actually, within those fabs, they do realize a technology where you need to actually repeat a number of process steps, and those process steps are typically it will come with a deposition of a thin film and then a lithography step where we put a resin, an exposure, and then develop the resin in order to punch some holes in it. And then there's a dry etch, for example, that is going to dig into the deposited layer. And then there's a cleaning. And this type of let's say, sequence of step will be repeated 40 to 100 times. And of course, every step needs to be aligned with the previous one in order to create a technology. So there are many, many, many process steps that are needed in order to realize or to create a circuitry on top of a silicon wafer. And so this industry is really growing fast. Those are some projections that they are actually from 2 years ago. So probably the projections are even stronger today. But essentially, between 2020 and 2030, this industry was projected to almost double in 10 years. In fact, there are many fabs that are coming online today. So those are 300 millimeter fabs, and more are coming. In fact, a lot of this growth has been fueled by the massive funding that actually came after the COVID period, with all the CHIP Act. So there was a CHIP Act in the US, but also in Europe. Japan also has been massively funding its industry, India as well. So a lot of money has been invested to increase the capacity of chip production. And so today, if I'm moving to those areas of concern, just wanted to take this picture of the planetary boundaries to try to place things a bit in perspective. So there are 9 planetary boundaries. I will not go into the details, but you can find climate change being one. But of course, we have other boundaries that have been across, for example, the biodiversity would be here. Novel entities would be related to the release of plastic pollution or PFAS, for example. And so when it comes to climate change, we know that climate change is on us, and the situation is not good. This planet is warming up, and in the case of the semiconductor industry perspective, so if we have anthropic emission of worldwide of 36 gigatons, so number can vary depending on the assumption behind, but the total weight of the ICT, so information communication technology industry, is about 1.2 gigatons, and that number is actually fast increasing, especially with the advent of the Gen AI technologies. And within this total footprint of the ICT industry, the making of the chips has been estimated in 2023 to be 175 million tons. And that is just to manufacture the chips. But you could also see that there are many steps up, let's say, downstream of that, plus also the life consumption or the use phase consumption of the chips. And then moving to another planetary boundary that is on novel entities. Our industry is using a lot of different materials, but also they are, let's say, releasing in the waste stream quite some material. And for example, one issue that the industry is facing today, like many other industry, is a problem with the PFAS. So PFAS are let's say a large class of material that that involve the usage of fluorine chemistry. And yeah, so PFAS today is a need to reduce the usage of PFAS and to reduce the release of PFAS. It is something that the industry is facing today. Maybe another area of concern will be the usage of resources, as this industry is actually using a lot of different materials from across the Mendeleev table. And actually, you can see here the let's say colored are the material that are let's say under threat in terms of either availability or sustainability. So also the industry is using high purity material and can be facing issues with resource depletion or geopolitical tension. Another concern for the semiconductor industry is the usage of water. And actually in this map, it is showing that there is actually expansion of the semiconductor industry in areas of, let's say, where the water scarcity can be a problem. And to make a chip, well, let's say foundries are actually consuming quite some water, so it is also a point of attention. So from so of course, all those sustainability problems have been recognized, and especially the climate change one. And so there has been commitment from multiple companies across the board to address these problems. And so from across the board, you can see a company like Apple who has been unveiling the first carbon neutral product, but you can also see from a foundry like TSMC to accelerate the switch to renewable energy adoption, but also suppliers to those foundries like Air Liquide or ASM also making a commitment towards to reduce climate change and to reduce their impact. And this is actually a report that was actually published by the SEMI Industry Consortium in 2024, and that is about the decarbonization of the industry, trying to establish a roadmap for decarbonization, try to understand where the industry as a whole is going. And so if we are looking at this plot here, let's say this trajectory would be the ideal one. That is the one that's respecting the Paris Agreement. But as a matter of fact, the business as usual trajectory has been computed to be the top one here, where at Horizon 2050, the industry would be actually producing a total of 168 megaton, and that is for scope 1 and scope 2 only. There is no scope 3 included in those projections. And then if we take into account all the pledges from all the different players of the industry, as I showed a few examples in the previous slide, actually there would be a faster decarbonization of the industry, and it would be actually following this trajectory. That is the trajectory that is including the decarbonization targets of the industry, and you can see that there would be a peak reached in 2030 before a progressive decarbonization, reaching a total of 60 megaton in 2050. Just wanted to also flag the fact that this data has been computed, let's say, before the generative AI boom, that may slightly change the picture here, as the demand of chip may further increase due to that. All right, and then after this introduction, I'm now moving on to what, let's say, one branch of what we are doing in the SSTS program in imec, and this is about the modeling of the environmental impact of integrated circuit chip manufacturing. And the model is named imec.net zero. So it's both actually the name of the model. It's also the name of the web app that let's say that embeds the model and enables it. And so the web app, there is a version that's publicly accessible in this web address or this QR code. So everybody can, let's say, log in, and if you make an account, it is possible to get access to some of the data that I will show here. And so the reason why we launched this exercise, and that was actually about 5 years ago now, it was actually to get a better picture of what's the climate impact of making chips. And in fact, in this early paper in 2021, it was actually shown that if we look at the total Apple carbon emission breakdown, and so by total emission, we take into, or this paper was taking into account the manufacturing of Apple goods, and then the use phase of their goods, as well as the transport and the end of life. And this study shows that about 3/4 of Apple footprint is related to making of their product, and about half of this 3/4, so it's about 40%, a bit less, is related to the manufacturing of integrated circuits. And then another paper completely independent from that one, also showing here the footprint breakdown of a generic smartphone, again showing that about 70% of the total climate impact of that object, so cradle to grave, full life cycle, is related to the production of that object, and about half of that, so 38% of the total, is related to the manufacturing of the chips inside the smartphone. And showing that in those type of consumer goods, it accounts actually for the largest share of the climate impact and dominates over the product use phase. But now, if we want to start to get solid data in order to compute this climate change impact, you have multiple sources of data. You can look into the scientific literature. So there are multiple data points here coming directly from scientific literature, but also you can look into life cycle assessment database, like the GABI database is a quite known one for this type of data. But essentially, there's a lot of scattering, and that is due to the different scope, different source of data, different approach in order to compute the data. This plot is actually showing the global warming potential in kilograms CO2 equivalent per square centimeter of chip. So essentially, we normalize everything by the area of the chip in order to make it comparable. And this is across multiple technology nodes. The most advanced technologies are here. And those are rather old technologies that were first produced, let's say, about 30 years ago for 350 nanometer. Another source of data would be the reporting from the companies who are making those chips. So this is in the right panel here, same unit. And here again, there's a lot of scattering of the data. This is through a number of years, and this is typically data that can be calculated or estimated from the CSR report of those companies. But very often the data comes from it is top-down data, so it's directly measured in the fab. But multiple difficulties come with this data. It's aggregated over the entire company operation. It is not given per chip or per node. It's actually given per year for the total company operation. So and also methodology is not clear on how those numbers are calculated. So all in all, there's a lot of scattering, a lot of difference in the data. It is difficult to find your way to calculate that. And so when we started the activity, We wanted to close the gap, provide quality, transparent data on the environmental impact, and especially model generic high-volume manufacturing plants. And so this is how imec.net zero was created. And the model really is a virtual fab model for environmental impact assessment that is actually enabling a bottom-up life cycle assessment to close data gap. And I will explain a bit more how we are doing this calculation. And then the analysis can be expanded. We can actually identify high impact problems, so really deep dive into what are the hotspots, where if you have a high impact for a chip, where exactly does it come from in the fab? And then we can also look into future technologies that do not exist yet today, that are not in production, but that will be in a horizon 10, 15 years, in order to try to understand what will there be their impact and how to influence it. And so we are using life cycle assessment. That is actually quite famous picture showing that life cycle assessment goes through a setting of the goal and scope, an inventory phase, and then an impact assessment. And then you need to use the brain in order to interpret the data. And so life cycle assessment applied to a virtual fab model like we do, it looks like this. We are looking into, as I said, high volume manufacturing of multiple integrated circuit technologies. So I mentioned logic already a few times, but we also look into memory technologies, but also RF imagers, photonics packaging. So a lot of different type of products that come out of the semiconductor industry. And we look at multiple nodes, multiple technologies, including future ones. We do express all the results in per wafer. So for example, kilogram CO2 equivalent per wafer, but we can also further functionalize that to look into, for example, per square centimeter, as I discussed earlier. And then we can characterize multiple impact categories. So climate change is one, but we can, for example, look into resource depletion or water usage. And then when it comes to system boundaries, we are going really to study everything that happens inside a fab. And we consider that as being the foreground of our study, where we collect primary data. But we have also a background part where if we want to get a full cradle to gate silicon chip manufacturing, that is actually everything that it took from the cradle, so really from the mining of all the different and the production of all the materials that are used in the fab, all the way to the finished chip, but not the use phase. Then we also need to gather background data to understand the supply chain of the semiconductor industry and to push that into the model in order to get the full representation. And so how do we compute the data at a high level? We have to gather process level data. So we are going to collect data on the tools. So the tools that are operating in the semiconductor clean room. So we gather information like what is the electricity usage of the tool, what is the water use, what is the let's say all the nitrogen, the cooling, the compressed air, let's say all the things that are needed in order to run a tool. We also collect data on the processes that are running on the tool. So for example, the gas consumption for a certain process, but also the waste that are being produced in the process. And we gather information on the materials that are used in those processes. And so with all this process level data, we have the ingredients for the virtual fab. And then we will actually build process flow. You can look at that like a cooking recipe, where in order to realize a certain technology, like a N65 and 65 nanometer logic technology, you need a certain process flow that will be a sequence of process steps. For the most advanced technologies, we are talking about 1,500 process steps, for example. And then in order to combine those two together in a realistic manner, we also need fab modeling, because it's not only wafers moving from one process tool to the next. There's a whole layer of infrastructure or facilities in the fab to support the tools. For example, there's a whole department that's doing abatement of gases before they are released by the fab. We need to take that into account. We need to take into account the way water is handled in the fab. Also, there are questions of yield because some of the wafers and some of the dies are being lost along the way, and we need to take that into account. We need to understand how wafers are also moving in the fab. So the fab modeling could be compared to the kitchenware. And so when we combine all of this together, we can actually come up with an inventory of IC chip manufacturing. And so inventory is really about the um, it's really in terms of physical flow, how much energy in kilowatt hour or how much of different materials in kilograms are being consumed in order to fabricate, for example, one wafer. And then we will do the characterization of the inventory. So we do the impact analysis, and characterization of the inventory is done using characterization factor. And for example, in the case of climate change, we are going to use values like global warming potential of certain gas to calculate in kilogram CO2 equivalent what is the uh, let's say what is the total equivalent of a kilogram CO2 that is released to the atmosphere in order to let's say by the gases that are being emitted by the fab for the direct operation, by the gas that are being emitted for the electricity supply, and also the CO2 emitted for supplying all the materials to the fab. And so when we do the full impact analysis to finally end up with a total calculation of the impact of integrated circuit chip manufacturing. And so those results, since we build them bottom up, they have a high granularity. So we can identify what are high impact steps. We can do sensitivity analysis on them, and we can also do projection and pathfinding by running future process flows in the model. Another way to look at the model, it is actually just to look, for example, it's an oversimplistic picture, but sometimes it helps people to understand how we do the calculation. At a process level, we know how much time a tool will be used, and we know how much electrical power is used by the tool. So we can actually, by multiply those two, calculate the electrical energy. And then for the impact analysis here, so this is the inventory value. And then we move to the impact analysis by, in this case, taking the carbon intensity of the electricity mix that's supplied to the fab in order to convert this kilowatt hour into a CO2 equivalent. So we have here a CO2 equivalent from the energy. And here another example that is to calculate, again, with the tool time and what is the flow of gas going into the tool for that process. We will get a total volume of gas. And then that gas, if it's a greenhouse gas, for example, will be used in a chamber. So some of it will be consumed, some of it will not be consumed. Sorry about that. And then the non-consumed gas will go through abatement. So some of it will be destroyed, some of it will not be destroyed. And the part that is not destroyed will be then for the impact analysis. We are going to use this GWP factor to convert the kilogram of gas released to the atmosphere into a CO2 equivalent. Of course, in order to build the inventory, we need those fab models. And so we have actually many fab models that are used to provide a realistic model for high volume manufacturing production. I just wanted to mention that the full methodology for imec.net zero is available on the public version of imec.net zero. So there's a lot more data that can be seen here. But so when we run the model, and we run the model actually across a progression of logic technology nodes, so today, 28 nanometer, that was first released in 2010. This is the node that is the most produced in the planet. So it's, let's say, the market dominating node 28 nanometer, and TSMC today is also producing the 2 nanometer node. That's the most recent and most advanced node that is produced today. So this picture is just showing, and this is really the total climate change emission in kilograms CO2 equivalent per wafer, just showing that there is with the progression of logic nodes, there is an increase in the complexity of the technology. Essentially, more and more process steps are needed to realize more advanced logic nodes. And so there is that there's really an increase in the total carbon footprint of the logic technologies as we are moving to more advanced nodes. And maybe here you see that there was a dip actually that happened around the 7 nanometer node with the introduction of a new technology that's called extreme UV lithography that actually managed to save quite a lot of process steps. So although the tool is very massive and consuming a lot of energy, it does help to save process steps and then to decrease overall the acceleration, let's say, of the footprint. And this picture is also then putting what I was just showing, the data I was just showing was just for logic technologies in perspective of other technologies. So you have here DRAM and 3D NAND. So those are memory technologies, and then a couple of nodes that are interesting for RF technologies. Just to show you also that for 3D NAND, that would be a flash memories, they do have a massive footprint per wafer of let's say more than 3 tons in some case of kilogram CO2 equivalent for the most advanced technology here of this NAND 352 layers. And if we actually convert this data, there's another way to look at it. Instead of CO2 equivalent per wafer, we can also do it in per lithomass per square centimeter. And that functional unit is useful in order to compare different technologies, let's say, regardless on the size of the wafer they were fabricated on and on the complexity of the flow, because by dividing by lithomass, you can actually just reduce it to a single step or loop that I was showing in the very beginning of my presentation. And you can see that there's a more or less a stable, let's say, gram CO2 equivalent emission per lithomass per square centimeter, let's say, across a lot of those technologies, logic, DRAM, RF, except for 3D NAND, because in the case of 3D NAND, you do less lithography, let's say, to pattern the full active layer stack. And then if we start to zoom into what's going on in a fab, we can actually split the results. Instead of looking at the full kilogram CO2 equivalent per wafer, we can try to understand from the analysis, okay, where is this footprint really coming from? And so we can divide it between different what we call process areas. So in this picture, for example, you can see what comes from litho, epitaxy, physical vapor deposition, chemical vapor deposition, wet, clean, dry edge. But we can also take the same picture and you see here the same wafer. We can actually also allocate it to what's going on in the subfab. And so what is the footprint coming from the incoming material? What is footprint coming from the power, from the chiller that are needed for cooling, for the process gas emissions from the ultra pure water manufacturing. And so this is really the strength of the analysis, to be able to decompose the impacts. Also, just keep in mind that in those numbers, there's a high dependence on the model parameters. So we have, as I showed, a lot of fab modeling parameters, and the picture could be quite different from one fab to the next. And here, this is just showing a generic picture of a generic high volume manufacturing fab. But now if we start to zoom in, we can identify different hotspots. One of them is the tool electrical energy. So tools are consuming quite a lot of power. A fab is consuming a lot of power. You can see here for this N28 example, we have about 30% of the total is consumed by the tool power. And by the way, in order to supply electricity to the fab, you will have also quite some power that is lost in the transmission. And so on this hotspot, and this is also showing a decomposition of let's say energy consumption by process area. It is essentially showing that electricity needs for semiconductor fab is really quite high. Tools are consuming power in the range of 55 to 50 kilowatt or even more. And high volume manufacturing fabs are using several hundreds of tools. So here, for the climate change impact, there's a high dependence on the electricity mix that the fab has available. We calculated that on average, let's say, semiconductor producing countries have a carbon intensity in the range of 500 grams per CO2 equivalent kilowatt hour, whereas the clean grids would be below 100 grams CO2 equivalent per kilowatt hour. And actually, this picture is also showing the case of Taiwan, where the electricity is actually not very decarbonated in that case. A second hotspot would be related to process gas emissions. So the ore industry is actually using a lot of fluorinated gases, and those fluorinated gases they have a high global warming potential. And so by higher, so the let's say when you release, let's say one kilogram of that gas, it will have a high climate impact. And this is mainly related to the dry etch process area, which is the one that is using this type of gases. And it has actually, we show here that there's about 50 kilograms in this 28 nanometer logic node example that is related to the direct release of those gases. So yeah, the industry use potent greenhouse gases. They have a strong radiative forcing, so it means that they will actually reflect a lot of the infrared emissions from the planet, and they have a very long lifetime. So in total, they have a high GWP, and here it is showing actually for four different gases used by the industry, the very high value of GWP. SF6 being actually the worst case, where you release 1 kilogram of SF6 is equivalent to 25 tons of CO2 equivalent. So there are technologies that exist and that are deployed in the fabs to destroy those gases before they are being emitted. And they have typically a DRE, so destruction removal efficiency of up to 95 to 99%. And not all fabs are well equipped in the sense that let's say the older fabs that have been installed or fabricated, let's say before the year 2010 or even older, they are not necessarily well equipped with abatement technologies. And here actually this Pareto plot is also showing from our modeling exercise what are the biggest emissions, and those are final emissions after abatement for the N28 nanometer example, where you can see that the most climate change is actually caused by the CF4 gas, followed by SF6, followed by this series of gas. A third hotspot is actually related to the climate impact of the upstream materials. So here, this is not an impact that directly comes from the fab itself or from the energy that the fab is using, but rather from the supply of the materials used by the fab. So it's very often referred to as being a scope 3 impact of the fab. And for example, in data already showed, the total impact of this material supply is estimated to be about 15% of the total. And actually, one of the big components of this impact is related to the supply of the silicon wafer. That is really the starting point of semiconductor manufacturing. You are going to start on the silicon wafer, and that one is a very high purity object. It takes actually a lot of steps in order to fabricate those monocrystalline silicon wafer, and many of those steps are very energy intensive, meaning that they will have also a high climate impact. But the silicon wafer is not the only source of impact. In fact, a semiconductor fab has a big bill of material. It's using a lot of material across the board. We have about I believe today something in the range of 150 to 200 materials in the bill of material. A lot of those materials have very high purity requirements, and so high purity means again a lot of energy needs to be invested in order to purify these. And let's say one of the main difficulties in estimating that impact, it is to collect the right data from very vast supply chain. So anybody who is familiar with the scope 3, let's say computing, knows that this problem can be complex. And finally, and that's the last hotspot I wanted to discuss today, it's related to cooling. And again here, there's a lot of heat that's generated in the fab, and that's related to the fact that since it consumes a lot of electricity, that electricity at the end of the day ends up as being heat that needs to be removed. And for example, a lot of the heat is being removed by chillers, and so there's a whole cooling water that is, let's say, process cooling water that is needed at facility level in order to remove the heat, and that is actually consuming energy. It is actually a heat management in the fab is a complex thing. Um, and that is actually using significant energy, but also water, because, for example, typically a fab is going to use cooling water, um, sorry, cooling towers where the heat is being removed through the evaporation of water. By the way, also chillers are very often using fluorinated heat transfer fluids, and those fluids themselves, they have a high global warming potential, but they are also PFAS materials. So this is also posing another type of problem here related to these novel entities that I was mentioning when talking about planetary boundaries. So finally, how do we address all those different hotspots and let's say more? There are, let's say, multiple topics for research. And I would say in the SSTS program, one part of the program is about the modeling and understanding what the problem is about. The other part is about doing research in the R&D fab of imec in order to address the hotspots and to address the most pressing problems. And I would say probably one good way to approach, given the complexity and the wide range of things that could be done, this marginal abatement cost curve is actually an interesting approach to it. And I would refer to this paper that has been computing multiple marginal abatement cost curve analysis for different fabs. And here this is a plot that's directly coming from that paper, showing the case of Micron. Micron is a memory foundry, where they show essentially on the y-axis you have the cost of, let's say, reducing the problem or addressing the problem. And and that would be actually in dollar per ton CO2 equivalent that's being saved. And then here on the x-axis, you have the total amount of CO2 that will not be emitted if you actually realize this improvement in the fab. And essentially, the ideal situation would be to be in a win-win position that would be actually with a negative cost where you actually save money, but also you are able to abate a lot. And for example, the biggest abatement possible, so the biggest area in this MAC curve is about process optimization on improved tool efficiency. Essentially, if you make your tool more efficient and you have actually process optimization to use less resource, use less energy, you will do a lot of saving. That's going to save money, and that's going to save CO2 equivalent emissions. So there are win-wins through energy efficiency, tool upgrades, through smart processes, so optimization, through leak reduction, and through waste recovery. But there are also other areas where you do have a cost environment trade-off. Those are areas where you have actually a positive dollar cost that can lead to significant savings, but you need to invest, and that's going to cost you money. This is, for example, to abate gases. I mean, gas abatement, it's really an extra cost that foundries have to pay in order to not release those gas. But more generally, waste treatment is a cost. The usage of renewable electricity can be also a trade-off, can be an extra cost, but also electrification of some process in order to reduce the usage of fossil fuels. But there are actually really there are solutions. Decarbonization of electricity supply and of the supply chain is, of course, something to pursue. Full abatement deployment is really needed. Replacement of material to actually use a material with lower impact. Process optimization, facilities optimization, R&D. There are many options, but really one driver, and that's really what we hear also from our partners in SSTS. We need to have economic viability. So we need to have return on invest on the innovation that's being done. Otherwise, it is very difficult to justify today the innovation. Okay, with this, oh yeah, maybe the last box here to comment on those solutions. It is really important to mention that this industry is really complex, and due to the complexity and the need to yield at the end of the day, the industry is really risk averse, and also the level of confidentiality is really high. And so the R&D horizon is really long and primarily impacts future technologies. In the sense that today, for example, imec is working on technologies that will come online in 5 to 10 to 15 years. The importance, there's really since waste usually represents a cost, regulation is important in order to motivate the different players to address the waste reduction. And finally, it is important to, when we are trying to solve one problem, to not create other problems. So life cycle thinking is something that we always advocate in the program, and also to avoid to have a pure climate-centric view to R&D and to embrace more impact categories. All right, and then moving forward, I just wanted, before I'm closing the talk today, wanted to say a word about environmental scoring as one way to also guide innovation in the field. And so we call that E-score. So E stands here for environmental score. And one thing is that as a program with limited resources, we are not able to solve a lot of the let's say the challenges that or the sustainability challenges that are faced by the industry. And in fact, the environmental concern should become the concern of all the R&D engineers that are innovating tomorrow's technologies. And so in order to try to influence their work and to drive a maximum impact on the industry, we are thinking about the E-score. The E-score would be actually an environmental metric that would come to complete the PPAC scorecard that is usually used in order to evaluate innovation performance in the industry. So PPAC stands for power, performance, area, and cost. And so we want to add a E to it. But in order to do that, we need to define the right metric. So how do we measure environmental impact, and how do we try to communicate on that in a way that is understandable to people and to engineers? What are the tools that are available in order to calculate this? So we need a platform for E-score quantification that is user-friendly. So people are actually motivated to use it. And then we also need to disseminate this. And so we are working on the E-score methodology. And that E-score methodology is actually based on the imec zero model that I just showed. But instead of doing it on the full technology like I showed so far, the idea would be to do it at almost a process step level. So to do a mini lifecycle assessment on a single process step, using imec.0 to establish the inventory. And then we would be relying on the EF, so the environmental footprint 3.1, for the impact analysis of this. And this graph is actually showing a methodology in order to calculate a single score from a full impact assessment. And so the proposal would be to first go to an inventory to actually calculate at a single process step level what is the inventory, how much kilogram, how much energy is being used, to then do the impact characterization. And we would do that across 16 impacts of the EF 3.1 framework. And then we go through a phase of normalization and of weighting in order to compute a single score at the end. And so the point is that if we only report the final single score, it might not be very speaking to the process engineers or to the environmental engineers who are looking into the data. So the proposal is that we would report not only the final e-score, that can be useful for some audience, but not everybody, but we would report inventory value, impact value, and also the final e-score. And when it comes to inventory values, we want to report electricity usage on the process, the water that's being used by the process, all the material that have been consumed, but also all the waste that has been generated through the process. And this is just showing a few plots that could be generated from this inventory in a standardized way in order to provide the information for the e-score user. And we would do something very similar for the impact assessment, where we would actually report all the impacts, and in a way that lets people systematically compare the reference process, that will be this ref here, the outer line normalized here, versus the test process or multiple test process that are the improvement, or the ones that the engineers are testing in order to try to see whether they have a better sustainability or not. There are different ways to look at the impact categories. This is also a normalized way, normalized and weighted way in order to directly put them on the same plot with the same unit. And finally, we will move to a normalization weighting. So here, once we have all the impact categories, we normalize them, we weigh them, we sum them up in order to get a final score. And that final score showing that the reference process can be improved in the test process. So the e-score today is work in progress, but we are really gathering all the tools and methodologies, and especially we are testing the e-score tool with process and integration engineers at imec in order to devise the best way to calculate the e-score, but also to communicate the data in a way that's user-friendly for the calculation and understandable and interpretable at the end. The idea really with the e-score would be to come up with a final dashboard that would be as standardized as possible in order to make, let's say, understandable comparison of reference versus test, but also to be able to be portable from one institution to the next. And so with this, I just want to conclude. I hope I have shown in this talk a few take-home message that the climate change impact of the IC chip manufacturing industry is expecting to increase in the future. And so the industry needs to work hard to fulfill their pledges and to achieve net zero by 2050. That the impact of the IC chip manufacturing is one of the largest contributor to the carbon footprint of ICT devices. And the reason behind is that it's due really to the complexity of those objects. They are ultra low entropy, so they're very highly manufacturing tiny objects, and they come from a very complex value chain. In fact, if you calculate the carbon footprint of a chip divided by the mass of the chip, you get to extremely high ratios in the tens of thousands. So that's on par with gold, for example. The carbon footprint of gold per mass of gold is actually extremely high one. IC chip have an equivalent type of footprint. It consumes, and this is really due to the fact that it consumes massive amount of electricity and high purity materials. And then the total climate change impact of IC manufacturing, it can be reduced by effective abatement of high GWP process gas by the usage of renewable electricity, or at least non-fossil based electricity. There's a need to defossilize the supply chain as much as possible. And finally, the adoption of environmental scoring metrics early in the technology design phase may help also to steer this big giant boat into a direction that is more sustainable. And so with this, I want to conclude to acknowledge all my colleagues, but also the partners of this program who are funding it, as well as two European funding projects, FAMES and Genesis, that are also supporting this work.
Thank you so much. This was so informative, and we have a ton of engagement. So I want to start by asking Cedric if you have a hard stop at 8 p.m. for you, or are you okay to take a few questions over time?
No, it's okay. No problem.
Okay, great. So everyone, I know everyone on the meeting might have to jump to another meeting. This is a recording and I will be posting it on our YouTube. So if you can't hang out for questions, we will be answering them here for the next 10 or 15 minutes, and then that'll be available. So let's get started. So the first question, Cedric, is if whether or not you're able to share these slides. I wasn't sure of that answer.
I will share, let's say, the vast majority, yes. I will have just to check that there's
Yeah. So
no
Cedric's
data
going
that.
to, yes, he'll double check and get back to me.
Yeah.
If not, I will again post the video to YouTube so you'll have access to photos of the slides as he's clicking through. So if available, I will make sure to include that in our blog post on this talk. Otherwise, you'll have access to the link, which we'll share via LinkedIn. Okay, I'm going to answer that one. Question number one, is chip manufacturing or manufacture getting more in E-intensive per centimeters squared? And I think this was one of your earlier figures.
It is certainly, if you wait, I just try to find a way to quickly move through. Coming back to this one. Um, so essentially, the question would be, if we use a functional unit, that would be kilogram CO2 equivalent per square centimeter. And the answer is yes, certainly. But it's always a complex question, because when you it let's say when we cannot just divide by the area of the wafer. The wafer is going to be cut in order to recuperate a certain amount of dyes. Some of those dyes are going to yield, and some are not going to yield. In generally speaking, the bigger the die, so if you actually make a very large chips, the yield is getting worse. And so the kilogram CO2 equivalent per square centimeter obviously is going to increase across generations. So definitely the footprint per square centimeter for 2 nanometer technologies is larger than for 19 nanometer. And that's because there's more processing that's done to create, let's say, the same area of wafer. But also, if you now try to create chips that have a very large area, you are going to lose more of them along the way. And so if we also, if we take a single technology like 2 nanometer, and then you make a 1 by 1 millimeter chip, you make 10 by 10 millimeter chip, and then you make the biggest you can, 26 by 33 millimeter chips, the yield will be worse on the bigger one, meaning that the kilogram CO2 equivalent will also be higher on those bigger chips, because the yield is worse. I hope I'm more or less clear in this answer. So it's a dual question. It increased due to technology complexity, but chip size also plays a role in the areal impact. So today, as the industry is moving towards a GPU, I mean, GPU is using pretty large chips of complex technology. So those chips have a very high impact. And it is the hope that with the advent of chiplet technologies that let you combine, let's say, multiple chips, but they can be smaller with a better yield, and also better functionalized to the exact need of the function they are to serve in the chiplets. That you are able actually to revert that trend and to better use the silicon, in fact.
Thank you. Our next question is, do you have a timeline for including the 10EF 3.1 impact categories in output?
So it was actually a recent release of the SSTS program. Now we have the 16 EF 3.1 impact categories are available in imec.net0 for the program partners. When it comes to the public version, today we don't have an agenda on that. That's not something um, I can answer regarding the public version. Maybe in the future, this is also something that we enable. So today in the public version, there's a limited set of impact categories that we can look at.
Thank you. Our next question is that you showed imec as having both gate-to-gate and cradle-to-gate models. For any studies currently using the imec model and LCA studies, are the values for the impacts based on gate-to-gate or cradle-to-gate?
It's always cradle to gate. As a matter of fact, maybe wait, I'll just go back to the scope diagram here. Essentially, we use this distinction just to distinguish the foreground, which is really the area where we are using primary data in our LCA. So this is really data that's collected, for example, in imec Fab. But we also have been receiving data from our program partners. Essentially, this is what we call primary data. So this is really data that's representative and that we can trust for the LCA. Whereas what we call the background, this is really data typically that would come from EcoInvent, that, through a standardized LCA practice. Of course, we are not able to fully connect all the EcoInvent data is always satisfactory, given the high specificity of some of the semiconductor materials. And so very often let's say we add a layer here where we try to build the best proxy possible in order to represent the data from the supply chain. But essentially, this background is really integral part of imec.net0. And whenever we are reporting results, the results are going to encompass, let's say, the full cradle to gate analysis, all the way to the making of the die. So the wafer, certainly the die, but we also have within the scope and the modeling that we do a lot of activity on packaging, because packaging is a zoo of technology. There's a lot of stuff also that's going on, let's say, downstream of the foundry, that also involves a lot of resources, both in terms of energy and material. And so we are also in imec.net0 developing a lot of different modeling of packaging technologies, but that is not available today in the public part of imec.net0. It is available to the program partners.
Thank you. Our next question is, given that most of the manufacturing information from companies is proprietary, how have the fab models in net zero been validated?
So as I said, on the foreground, we are collecting data from multiple sources. In fact, I have to say that we were lucky at imec, because we are really, as a R&D research center, collaborating with pretty much every company out there, really sitting at the crosspoints of all those companies, and having also access to our own fab. That is a big fab that is actually filled with let's say, industrial grade equipment. We have direct access to data. And so the data, as I said, we are, for example, doing measurement campaigns on some of the tools in the fab in order to collect the data. And we also collecting data that our partners are kind enough to share with us. And then when it comes to validation of the results, first thing I wanted to say is that imec.net0 model is being audited, and we have an audit once a year by a Fraunhofer. That has been, let's say, we have been opening the full model, opening our books. Essentially, they have looked into that, and let's say provide let's say a verification and a certification that the model is doing what it is supposed to do. And then besides that, we have foundry partners, again, who have been kind enough to provide some benchmarking exercise. So essentially, for example, calculating for a certain technology, what is the footprint? with fab modeling parameters that correspond to the reality of a fab, of a real foundry, and then comparing that to the results that these people are able to compute based on a top-down exercise. So typically fabs are able to compute their carbon footprint by looking for certain fab, how much electricity has been consumed, what is the procurement of that fab, and then compare that to the full year production of the fab. And so comparing imec.net0 bottom-up numbers with top-down numbers from foundry partners has been a very useful exercise for us to calibrate and to understand where the problems were. But so today, imec.net0 has been in existence for about 4 years, and a model in development for longer. So today we have the let's say the confidence that we are reaching numbers that are generically representative of the industry.
And Cedric, I'm going to hop to the next question because I think you might have just answered this as well. We were asked, I see that the methodology has been independently reviewed. Is there a plan to have the data reviewed as well? And what is the timeline for this? So that is kind of what you were just talking about as well, right?
Indeed.
Okay, perfect. We're gonna skip that one. Okay, great. So how does imec envision these models to become useful for the average LCA practitioner? The average user doesn't have die size information, doesn't know which fab their IC was made in, and so forth. Plus, the practitioner must add a model for packaging as well. The current option is to use LCA for experts, which has outdated technology nodes. But at least an average LCA practitioner can identify an appropriate proxy for their ICs being used in the product. So, how does imec envision supporting the LCA industry with more accurate IC and photonic product models that a typical user can actually use? That was a long one.
No, it's a very good question, and in fact it's it's really to the point, huh? How to make this data more actionable. Clearly there's a gap. It is a very complex. So anybody who has to do in a carbon accounting exercise and where your company is putting a product on the market, and then your job as a LC engineer in that company is to calculate what is carbon footprint. You are going to look at the product, and then there's a number of chips that are going into the product, but it is very difficult to understand what's inside those chips. And so there's a whole investigation that needs to be done in order to understand, okay, that package, this is that technology. Inside the package, you have so many chips of that particular technology. This is the size of the chip. And maybe you can do that on a single chip. Good luck to do it if your product is or your company is using hundreds of those chips. So we do recognize that gap, and we see that today in the program partners who are mainly who have been funding this research and who are using the data. These people have the capabilities to put sufficient manpower, let's say, and resources in order to do this investigation. But this is not helping necessary smaller system companies who don't have all those capabilities. It's a recognized gap today. Um, and so we are investigating, let's say, multiple ways to help those people through making the data that's in imec.net0, let's say, more broadly available to the public, and in ways that are, let's say, if I may say, more user-friendly. So but this is really, I would say, what work in progress today in the SSTS program. So I would say, yeah, this is yet to come online, and we are still to communicate on the exact format where the data will be more available. But clearly it's a recognized need, huh? That die data needs to be attached to a package that needs to be attached to a product. So let's say today we are helping maybe 70% of the effort, the 30 last percent effort. This is still let's say future work and future development on how to help there.
Thank you. Our next question is why is the infrastructure excluded? Fabs are one of the shortest lived industrial buildings.
Um, Very good question. Um, when you start to do a LCA, it's in the scope exercise, you start to exclude things simply because you have no information about it. But then, of course, to do things a bit more rigorously, we need to try to very roughly estimate what would be the total importance of those two items. What is the footprint of making the equipment that are in the clean room floor? What is the footprint of making the infrastructure, making the buildings, but also all the facilities that are inside the fab? And then, of course, the footprint of making those need to be distributed over maybe the lifetime of the fab. So there's a whole debate, of course, on how you are going to allocate that footprint to a single wafer that is produced during the entire lifetime of the fab. Um, the initial assessment was showing that the infrastructure construction footprint is actually quite negligible. So if it is allocated to the total lifetime of a fab, and typically fabs are built to stay. They are actually a closure of a fab is actually a rare event. Fabs that have been built 30 years ago are still there and are still producing today. So they have fairly long lifetimes. When it comes to equipment manufacturing, equipment may need it is evolving. Our initial assessment was showing that this could be significant, in fact, but clearly there's a lack of data on this topic, and really I would well, some of the equipment manufacturers have been actually doing a good progression in order to provide such footprints, but that is not something that we have been able to insert in the model today. Probably work for the future, and probably this is something that is not so neglectable, but also not that easy to compute given the complexity of those equipment. I hope this answered the question.
Thank you. This has been very informative, and this question asker is curious on the sources of primary and background data used in the tool and its representativeness across the industry.
All right. So I already mentioned where we get the foreground data. Um, so I would say we are, in terms of representativeness, imec fab is not a production fab. We are R&D fab. It means also that typically in a production fab, the tools will be grouped by what so-called tool groups, where you have within a tool group, let's say dry etch tool group, you will have 5 to 20 times the same tool. So the same tool is really reproduced multiple times, and those tools um, serve as backup to each other, for example, and also are there to really make sure that the production is very stable. In imec, we don't function this way. We essentially have we receive all the beta tools before they go to production. They will go to validation in imec fab, for example. So we have tools that are sort of industry ready, but they are quite unique versions of them before they are being sold or installed in the industry. And in that respect, I would say that the data that we derive on the tool is really quite representative of what an equivalent tool will look like in a production environment. But of course, it's not fully optimized to a level that exists inside the fab. But this is sufficient to be representative. It's definitely not as if we were measuring the electricity consumption of a lab tool that would be let's say, a smaller wafer diameter and in essence, a much actually smaller tool that is non-representative of the industry. When it comes to background data, I also already mentioned that we are mostly basing the characterization of the inventory on eco-invent. But I would say that we do a lot of pre-engineering in the sense that there are a lot of chemicals that come into the fab that are very specific to the semiconductor industry. So we are going to do a modeling level to really best represent that chemical And then based on the RM method, if you're familiar with that, RREM, that is actually to then source what are all the components that are needed in order to make that chemical that goes into the semiconductor fab. There are also discussions with material suppliers in order to supply better models for the that are more directly representative of the semiconductor grade chemicals. But there, very often, one difficulty that we face is that those models are fully representative for climate change, but they don't involve the other impact categories. And so it's kind of difficult to plug those models into our model because it's the scope is too limited and is not compatible with our scope. So that's one of the reasons why we very often fall back on let's say LCA source data.
Thank you. Can a score including health impacts be done correctly? What do you do about discounting? I think any method has flaws.
I'm not sure I get that one. So on health impacts,
Yep.
well, I will take a joker on that one because I'm not sure I understood.
Okay.
I understood this one. Very sorry, and don't hesitate to send me an email if I'm not answering correctly.
Let's move on. I'm not quite sure either. So if the questioner wants to add clarification, you can do so in the same spot and it'll pop up at the bottom, but we're going to move on. We have six more. I know we're over time, so let's get through these last few. Is anything being done to consider heat pumps to return the heat back to the equipment from the fab?
Uh, I, I would say that there's a lot that's done in this field. And in fact, it was one bullet point here when I mentioned, I don't think I mentioned it during the talk, but there are multiple opportunities to valorize the waste heat through heat pumps. And in fact, as I was showing in this MAC diagram, marginal abatement cost curve, clearly this kind of improvement is really something that is a win-win situation where you can actually also gain money because you don't need to spend electricity or fossil fuels in order to generate heat. And also the subfab, and they are putting a lot of brackets, can be a place where there can be transformation going on. Whereas on the clean room floor, it is much more difficult to change things once they have been installed. But I would say today you can be assured that modern fabs that are being installed today, they have optimized already very much those type of waste heat valorization pathways, as well as the water, as a matter of fact.
Thank you. Okay, a few more. So, has stochastic multi-attribute analysis or SMA been considered instead of the single score?
No, and I would love to hear more about it. The
Curious.
topic of the single score is an endless topic here internally amongst the research folks. Everybody hates it for multiple reasons, and at the same time, we all do realize that we cannot just throw like 60 different figures to people and ask them to improve on all of them. And since my title is a manager, as a manager, I like to have like a clear KPIs, and I can take e-score as one KPI where I'm telling engineers, guys, you have to decrease that value. So it can be useful. It can be criticized very much in the way it's normalized, in the way it's weighted. And at the same time, if everybody agrees on the same method and on the same language, it might be actually a language we are able to speak. So no, I'm not familiar with the stochastic method you mentioned. I would love to learn more about it.
I will send you over some resources we actually have on the website. But a perfectly timed question, as we were just talking about the weighted e-score, which outside of imec stakeholders are driving you to spend time on a normalized and weighted e-score is the question, if you can share.
It's actually I think one of the original interest for the E-score was coming from the equipment suppliers. Maybe I can show a slide again on this because where should I go here? Because essentially, as I mentioned in E-score, you can see it as a mini LCA that is done at a process step level. Um, and in fact, the being able, I don't know if you run a dry etch design of experiment, and then you can do for every entry in your design of experiment, you can actually get an environmental assessment. It is actually very directly beneficial for the equipment suppliers who can actually also include that into the recipe development they do on their own tool. Because very often when an equipment supplier is selling a tool, they also sell a set of recipes. So for them, it is also one way to influence the sustainability in a positive way by having those type of methodologies to calculate E-score. So it was, let's say, one source of motivation, but I would say one principal source of motivation we have today in E-score development is actually coming from the public funded projects, where we do see in the public funded project a lot of different partners who are developing more sustainable solution. But what does more sustainable mean? It's actually a very good question. It's a complex one. If you want to answer it in the right way, you need to apply the right methodology. And so we have actually in imec become a partner that has the capability to supply this type of methodology to the other project partners, so they can actually calculate their, let's say, the sustainability impact of their invention, of the research that they are doing in the public funded project. And so today, eScore, for example, is a deliverable for the FAMES project that I acknowledge at the end. It's also something we are working on in this Genesis project.
Thank you, Cedric. This next question asks for comments on recycling. I'm not quite sure what they're referring to, so we can skip it unless you have comments on recycling.
Recycling is a complex topic, and maybe if I wait, I just to illustrate that, I would just go back to this cycle thing here because recycling is actually mentioned here. Very often when we talk about recycling, what people have in mind is the fact that at the end of the use phase of those consumer products, smartphone, server, whatever, you could actually let's say tear it down, recuperate the chips, and then valorize them again in this big loop. The e-waste is very difficult to recycle when it comes to the recuperation of, I don't know, some precious metal from within the e-waste. What you need to understand is that in the silicon chip manufacturing, we are talking about nanometer quantities. We are talking about tiny, tiny quantities that are added on a very small object. That very small object is then being, mixed with tons of other objects in order to create the final product. And so to recuperate nanometer quantities of a certain metal from an object that's already very embedded in a very heterogeneous, let's say, material set, it's very complicated to have a positive return on invest. So typically e-waste recycling will be done, but it will only be done for very few material that such as gold. Gold is used in packaging, and there it makes sense to recuperate gold. But apart from gold, to be honest, maybe copper, there are not so many metals that can be efficiently and economically recycled here. Another opportunity for recycling would be, let's say, at the fab level. To make a chip, you're actually going to generate a lot of waste. In terms of just mass, you actually use a lot of water. That's one thing, and you can recycle the water, and it's done in the fabs. But you also generate a lot of waste chemicals that are actually appearing in the fab waste streams, and there can be opportunities to recycle if we are able to segregate the waste as early as possible. For example, before it's being mixed with other wastes. There are opportunities there. It is complex. It is complex to set up because it's very often, and that's unfortunately with circularity, you directly go into the weeds of the complexity of that particular material stream that you want to capture. In order to devise a full circularity loop, you really need to go into the details of every step there. And that starts with where do we catch the material and all the technical questions that are going to follow. That will be but I would say there's more potential there to recycle fab waste. Um, yeah, and then you have some barriers that are maybe more how would I call that? Soft barriers, not technical barriers, but more soft barriers related to the perception of quality in a fab, where people trust more, I guess, material that are coming from a linear economy, coming from the supply chain. A question of responsibility, by the way, on the material suppliers are responsible for the quality of the material that are being used in the fab. So if in a recycling scheme in terms of responsibility, it poses quite some difficulties. So I would say more potential for fab waste recycling than the e-waste recycling. And I'm not meaning we should not do it, but I'm meaning there's more potential. And then there are, but also technical barrier, but also soft barriers to it.
Perfect. Okay, three more questions. Thank you everyone for your engagement and Cedric for your attention and all your explanations. Okay. This question is, will the imec.net zero models ever be incorporated into another lifecycle inventory database like EcoInvent or Sphera?
As I already mentioned in the previous question, we are thinking about it, but I cannot really further comment on that. We do realize that there will be a lot of value, of course, for this model to be more broadly available and to be, let's say, more easier to use for LCA practitioners.
Thank you. Given that demand is rising and impact of newer technologies is higher and higher, do you see any pressures pushing impact down? Is this a runaway rebound effect situation?
Sorry, can you repeat that one?
Yeah, of course,
So,
of course.
yeah.
Given that the demand is rising and impact of newer technologies is higher and higher, do you see any pressures pushing impact down? Is this a runaway rebound effect situation?
It's certainly a rebound effect. I mean, definitely, and they are. I would actually invite the person asking the question to look into the work from David Ball, who is a professor at UC Louvain here in Belgium, who has actually and his team have been publishing on the topic. But there is actually a mechanical rebound that's at play in the industry today, certainly. Yeah, we are. Yeah, I mean, I would say the IC chip technology in general is so effective in answering a lot of our needs that we are consuming more and more of this. Is this a runaway rebound? I am not sufficiently educated in the field to be able to comment on that one.
Thank you, Cedric. And this last bit, which I'm really interested in as well, is has IMEC published any citable reports with the information presented in these slides, or are there any reports or documents you'd like to direct our audience at?
Uh, Certainly. I mean, the first thing that can be done is to look at our websites because they are, as I said, the methodology is or the website of imec.net zero. On the methodology, the full methodology is available there with a number of sources. And I would say we do have a few publications. Probably we have actually the two most relevant papers that have been published on the topic are were published in the IEDM conference. So it's actually electronic device conference, which is probably the where as imec we can have the most impact because it's addressing directly electronics folks. And there we have a paper in 2020 and a paper that was published in 2023. So maybe if you are publishing those slides, I can also add those two references here on this slide so people are able to find them back. But both of them are, let's say, discussing the imec net zero model. Of course, the model keeps evolving. So the 2020 paper, they sort of date a bit, but still it's showing the foundation and where we started and where we come from.
Excellent. Thank you, Cedric. I'm going to be putting together a summary of this talk for our website, and I will make sure to consult Cedric with any links or maybe these slides, definitely the link to YouTube, and I'll make sure to put all that together for you. Thank you to our audience for being so engaged today. Cedric, you answered possibly a record number of questions. Thank you for your
All
extra
right.
time. Everyone was super engaged, and I hope everyone has a really nice day. And join us next month for our February Brown Bag webinar. Thank you, Cedric.
All right. Thank you. Thank you
Yeah,
very much.
bye.
Have a good day.